Now we are going to discuss the implicit function theorem, which is a lot like the inverse function theorem. It is, in fact, a generalization of the inverse function theorem, but it's a little bit complicated. So to describe what it's actually doing, I think we'd better start by reviewing a little bit some information about graphs and curves and surfaces. So let's recall. So let's let f be a function from the real numbers to the real numbers, or a function from an open subset of the real numbers to the real numbers. But since we're giving examples here, we might as well keep it from the real numbers to the real numbers to make our life simpler. Let's say continuous and differentiable function, so that things are nice. And then the graph of f, let's notice that R, we can call that R1, is going to be a one-dimensional subset of R2. And you all know what graphs of functions from the real numbers to the real numbers look like. You've been dealing with these things since you were in high school. But just to start out with, let's remember what they look like. Here is the graph of f of x equals x squared. And I'm sure there are all kinds of other functions that you could draw the graph of if I asked you to. But this is the chapter on multidimensional linear spaces, so multidimensional differentiable functions. So now let's let f be a function that goes from R2 to R, then, or rather R1. And we'll suppose it is continuous and differentiable and all that good stuff. Then the graph of f is a two-dimensional subset of R3. You need 3 dimensions, 2 of them to be your domain dimensions, and 1 of them to be your range dimension. So let me sketch an example of a 3-dimensional graph for you. Here's x, here's y, here's z, and here is the graph of let's say f of xy equals, let's say x squared plus y squared. And then if you visualize that, you get a two-dimensional surface. And if you track yourself down a nice 3D graphing program, you can plot graphs of all kinds of two-dimensional functions, and you'll see they all look all kinds of functions of 2 variables, and they all look like two-dimensional surfaces. And I encourage you to do this. It'll let you see what's going on. Now let's talk about something a little bit stranger. it's not stranger in an abstract sense, but it's stranger in that you probably have not drawn it before. You have not seen things like this. So let's let f be a function now whose domain is R1 and whose range is R2. So it's from one dimensions to two dimensions, not the other way around. And then the graph of f it's still one-dimensional. Your input still looks sort of like R1. You can still trace it out by drawing with one pencil. But now it's a subset, not of R2 like in our first example, but a subset of R3. You need one dimension for the input and 2 dimensions for the output. And let me try to draw the graph of one of these things. So here, let's say this is our x coordinate. And let's say f of x is, it's a vector now, so we'll say it is cosine of x, comma, sine of x. And then this, when you graph it, we start here at 1, 0. We move up to 1, 1 over at pi. And then this is going to trace out a sort of helical path through space. And I will give you a link to a Desmos sheet that lets you look at the graph of this thing. But you see, this is indeed a subset of R3, and it is one-dimensional. It looks like a one-dimensional path. I'm not going to draw a picture of the general case. I will just state that if f is a function from Rp to Rq, or if f is a function from x to Rq for an open subset of Rp, then the graph of f is a subset of Rp plus Q and is p-dimensional. We, of course, need f to be continuous and ideally differentiable for this to be a nice curve. So now let's talk a little bit about level sets. You might have come across these. I'll try to give you some familiar examples. So let's let f be a function from R2 to the real numbers. The level sets of f are usually, but not always, one-dimensional. And they are, of course, always subsets of R2. And to give you an example that you are familiar with, so let's let f of xy be x squared plus y squared. Then the level sets of F, of course, are the circles. Here is the circle F equals 1. Then you can have a circle with bigger radius. That would be the F equals 4 circle, and so on. And you'll notice that this is the circle x squared plus y squared equals 4, so f of xy equals 4. That's why we call it a level set. Another set of level sets you may be familiar with are the hyperbolas. This is f of xy is equal to x squared, now minus y squared. And then our level set f equals 1. Notice that our level set f equals 1 is now a hyperbola. It's suddenly not connected. Then the level set f equals 2, similarly, is a two-sided hyperbola. And the level set f equals -1 is a hyperbola going in this direction. And let's have a look at level sets in more dimensions, or you can think of them as solutions to algebraic equations. So let's say we've got a function from R3 to R, then the level sets of f are usually, but not always, nice two-dimensional. It's 3 minus 1 equals 2 is where the 2 is coming from, subsets of R3. So, for example, let's do the spheres because I think I can draw them. F of x, y, z is x squared plus y squared plus z squared. Then the level set of that would be a sphere. So this, for example, would be f equals 4. Now let's talk about a vector-valued function. So what do level sets of vector-valued functions look like? Let's let f go from R3 to R2 be given by something I think I can draw, f of x, y, z, x squared plus y squared plus z squared, comma z. So the input has 3 dimensions, the output has 2 dimensions. And the level set let's say f of x, y, z equals 2, 1. Now what happens is the first component of this is going to be the intersection of 2 surfaces that you're used to. So x squared plus y squared plus z squared equals 2. That is still the sphere. And then z equals 1, that's going to be a flat plane. It's, of course, infinitely big, so I don't want to draw the whole thing. And then the intersection between the two, the set of all x, y, z such that both of these equations are true, that's going to be this circle up here. So this is equals to f of x, y, z equals 2, 1. The z coordinate is 1, and x squared plus y squared plus z squared equals 4 is 2 equals 2. Sorry. So that's the circle of the sphere of radius root 2. So that is a circle. That it is one-dimensional. So remember we said that if you've got a continuous differentiable function f from Rp to Rq, then its graph is always going to be a p-dimensional subset of Rp plus q. And I don't want to tell you what p-dimensional means precisely. It's going to match up with your intuitive notion, but just point out that the graph of a smooth function is always going to be p-dimensional. Things are a little bit more complicated when talking about level sets. If f is a function from Rp plus q back to Rq, then the level sets that's f inverse of a point C, that's the set of all points x, let's say x in Rp plus q, such that f of x equals c. That's the set of all solutions to the equation f of x equals c, are usually p-dimensional subsets of Rp plus q. But not always. So let me give you some examples. So f of x, so here's the graph of the equation x squared plus y minus y squared equals 0. Notice that this is a big cross. It's got this one point in the middle where we've got two lines crossing each other, where it's not locally one-dimensional. It doesn't look like a nice one-dimensional curve. And there are other examples like this. For example, if you take the equation x minus 3 squared plus y minus 1 squared, if you take that and set it equal to 0, the graph of that is a single point, which is not one-dimensional, it's zero-dimensional. Or if you take the graph of x squared plus y squared equals -1, the graph of that is the empty set. There's nothing in it. So that's certainly not a nice one-dimensional subset of R2. And you can do this in higher dimensions as well. So the question we're answering in this section is as follows. Let's let f be a function from Rp plus Q to Rq. And the question is, when is f inverse of a single point a p-dimensional subset? And in particular, when is there when is the inverse the level set? When it is it the graph of a function? Such that f inverse of C let's write out what that equals by definition of f inverse. That's the set of all points x, y in R p plus q. X is in Rp, y is in Rq, such that f of x, y is equal to C. We will be using slightly different notation for points in Rp plus Q going forward, but I don't want to explain it just yet. So when is it that this set is equal to the graph of H? That is the set of all x, H of x, such that x is in Rp. So answering this question is the point of section 6.9. Section 6.8 was the inverse function theorem. When can you say this function with an invertible derivative is at least locally an invertible function? This one now, it's I've got a set in Rp plus Q described algebraically. If you've got an equation for a set, you can always write it as the level set of a function. Just shove everything to one side of an equation. And we're trying to ask, when is this set described algebraically? When is it the graph of some function h? Now, to answer this, we're going to need some notation. So we're talking about functions from Rp plus Q into Rq. So we're sort of breaking this up into the first P derivative coordinates and the first Q coordinates. So here's how we're going to write this. If x is in Rp and y is in Rq, then let's say there's two ways of writing this. Your book likes to write this as x direct sum of y. And if you're already familiar with direct sums, if this is a notation you know and love, you're welcome to use it. If you are not already familiar with direct sums, I think it's a little cleaner to just write this as an ordered pair xy. It's not quite an ordered pair, but it's a mild abuse of notation, but I think it makes things a little clearer. These both represent this point in Rp plus Rq. It's the point with coordinates x1, x2 up through xp, and then y1, y2 up through yq. So You can so you can think of it as an ordered pair x, y. You can think of it as a direct sum x plus y, or you can think of it as a point in Rp plus Q. You can think of Rp cross Rq, the Cartesian product. You can identify that with Rp plus Q. So we're going to write points in Rp plus Q this way. So now let's notice a pretty straightforward fact. If, let's say, T goes from Rp plus Q into, well, into any vector space, but we're only going to really need this mapping into Rq is linear, then T of the point xy, that's T of the point x0 plus 0y, that's T of x0 plus T of 0y. So we can break up this. Notice that E of x0 is a linear function in x, and T of 0y is a linear function in y. So any linear function defined on Rp plus Q, we can write that as the sum of a linear function on Rp plus a linear function in Rq. So we are going to define the following notation. If T going from Rp to R plus Q to Rq is linear, then we're going to let, your book calls this T sub P of x. I think that is actually absolutely terrible notation, because sometimes we care about the case where P and Q are actually equal to each other. So I am going to call this TL of x for the left-hand part. That is just T of x0. And this is defined for all x in Rp. And then T sub R of x, which your book insists on calling T sub Q of x. That's T of 0y for all y in Rq. And it's not too hard to check that. If T is linear, then so are the left bits and the left and right operators. And we can put this together with our previous fact. And write any linear operator in terms of these two pieces. Now we are going to state the implicit function theorem, which is the theorem that answers this question from the previous slide, that tells us when we can write a set, the level set of a function, as the graph of some other function. So this is theorem 6.9.2 in your book. So here is the statement of the theorem. let's let G be a subset of RP plus Q that is open. And let's let capital F be a function from G to RQ be continuously differentiable. And then we're going to let A, B be a point in G. And we're going to require also that f of AB equals 0. If we happen to be at a point where f of AB equals some other number equals 87, you just replace f by f minus 87. We only really care about level sets at 0. And now we've got a condition that's going to look a lot like the condition of the inverse function theorem. And there are deep connections between this and the inverse function theorem. So let's suppose that we take the derivative of f at the point AB. That is a linear operator which has domain RP plus Q and range Q. So we don't want to say that that thing is invertible. It's going between spaces of different dimension. But if we grab the right side of it, that is the bit where you feed in just the second batch of coordinates, then that's something that does indeed have domain RQ, which is the same as its range RQ. Let's suppose that is invertible. The conclusion is that then there are omega and W and H such that this is going to be a very long list of properties because I'm trying to break it down pretty far. So omega and W are both open sets and H is a function. So we're going to say that omega is a subset of RP that is open and has A in it. And W is a subset of RP plus Q that that is open. That is open as subsets of RP and RP plus Q. If you put RP inside RP plus Q, then nothing's open. And we also say that AB has to be a point in W. And then H is a function whose domain is omega and whose range is RQ. And we've got that H of A is equal to B. We've got that H is continuously differentiable on omega. So we've got a nice function with the right output at A, and such that we can write this two ways. if x is in omega, then we've got that h of x is in W. And I suppose I really want to specify that W is a subset of our open set G where F is defined, which implies this thing I said, that it's a subset of Rp plus Q, but is more specific than that. So h of x is in W, is in G, is in the domain of F, and f of x, h of x equals 0. And moreover, if we've got that x, y is in W and big F of x, y equals 0, then y is h of x. So we're saying that if we've got this nice function f, the 0 set, the level set f equals 0, that is precisely the graph of some nice function h. That is, x h of x is in the level set, and conversely, everything in the level set is in x h of x. I suppose in this case, I should specify x is in omega and y equals h of x. Yeah, I said f of x, y equals 0, f of h of x, h of x equals 0. I, of course, meant that f of x, h of x equals f of ab, f of x, y equals f of ab. The way your book likes to state this, requiring that f of a be equal to 0, and you can make that be true just by adding a constant, but I'm going to state it this way: f of x, h of x equals f of a b, which may or may not be the 0 vector. It turns out this theorem is equivalent to the inverse function theorem. That is, there are reasonably straightforward proofs, arguments that say if theorem 6.8.2 is true, then theorem 6.9.2 is true, and if theorem 6.9.2 is true, then so is theorem 6.8.2. And we, in the videos, we are going to prove one direction. We have already proven theorem 6.8.2, and we're going to use it in the next video to prove theorem 6.9.2. On your homework for today, I think I will have you prove the converse. I will have you assume that theorem 6.9.2 is true and use it to prove theorem 6.8.2. Now, we've already got a proof of theorem 6.8.2 of the inverse function theorem. We don't already have a proof of the implicit function theorem, so this isn't technically telling you anything you don't know, but I think it's good to work through the argument that the inverse function theorem is a special case of the implicit function theorem to, if nothing else, it'll give you familiarity with the implicit function theorem. It will let you see what is going on. Let's have an example of the implicit function theorem, and let's see if we can see what all the pieces are. Let's let P be 1, Q is going to be 2, and we'll let G be R1 plus 2, also known as R3, and F is the is going to be the function defined by f of x, y, z. This is going to be a vector-valued function, so its first component is going to be x squared plus y squared plus z squared minus 49, and its last component, we'll say that's z minus 3. And I picked this particular function, of course, because I am not totally terrible at drawing planes and spheres. So here is our x, y, and z coordinates. Then here is our sphere where the first component where f1 is 0, that is of course a sphere. Then we've got our plane where our second component is 0. And they intersect, of course, at this circle here, this circle where all of f is 0. You can write this as f vector equals 0 vector. I'm sure some of you will be more comfortable writing it that way. So we've got that f of a, b1, b2. We saw that was a squared plus b1 squared plus b2 squared minus 49, and then b2 minus 3. And then we remember how to if we've got a continuously differentiable function, which this is, it's got continuously differentiable partial derivatives. We have that by theorem 6.5.7c. We have that df of a, b1, b2. This is a linear operator, so let's write what the input is. Let's call it UVW. This is a big matrix. It's partial f, partial a, partial f, partial b1, partial f1, partial b2. That whole matrix times the vector u, v, w. And then let's go ahead and evaluate our partial derivatives. This comes out to 2a, 2b1, 2b2, and then 0, 0, 1 times UVW. And then when we break up our DF into two pieces, that's basically slicing a square piece, this right-hand square piece and the left-hand whatever rectangle that ends up needing to be. Yep. So our right-hand bit, DF of A, B1, B2, the right-hand bit of VW, that's just multiplication by 2B1, 2B2, 0, 1, that is invertible as long as B1 is not equal to 0. So if for example, pick our AB point to be 2, 6, 3, then f of AB is indeed 0, the 0 vector rather. So let's draw a cross section of what's going on. Here is our x coordinate, here is our y coordinate, then the z coordinate is coming straight out of the page at you. And there is our level set. And here is our point. Our point 2, 3, 2, 6, 3. And then omega would be a region like this. So it is an open subset of R such that at F such that this curve, or at least this part of the curve, is the graph of a function. It is a two-dimensional graph we're projecting downwards, but nonetheless, this is a graph of a function, and then our region W would be something like this, only in 3 dimensions. So it would project up in the z dimension as well. So that is the picture of the implicit function theorem that I'd like to be in your head.